I'm going to now record the end of the chapter that starts at 10.7 about organometallic reactions. I've mentioned this term before. Organometallic means that it's molecules that contain carbon and also metals, and there's covalent bonds between the carbons and the metal atoms. And the first one we're going to look at is called a Grignard reagent. Now remember that if you have a carbon to halogen bond, it's polarized toward the halogen because the halogen is more electronegative. And this chapter has been about organohalide type compounds. Well, we've learned in the past about alkali metals and alkaline earths. Remember, this is column 1 and column 2 of the periodic table. And those metals are very readily able to give up an outer shell electron or two, depending on which column you're in. So we can react an alkyl halide with magnesium metal, and this little zero here means it's elemental metal. Magnesium metal, we use what are called magnesium turnings, which is like if you drill a hole through a piece of metal, it makes little curls of metal come out of the hole. So that means it's got more surface area than just a slab of metal. And it's also because it's actually pieces of metal as opposed to a powder, it's easier to keep it from oxidizing if you use it as little pieces of metal instead of powder. So you put these little pieces of these turnings into a flask with your alkyl halide, and there's a solvent involved typically, and it will make this complex called a Grignard reagent, and this is named after this person, Grignard, who discovered this. Now in the process, the magnesium is getting oxidized, so it's going from 0 to officially +2 is its oxidation state in this compound. And that causes both the carbon and the halogen to now have negative characters. So effectively, as the magnesium gets oxidized, the carbon is getting reduced. And so what can we do with that? One question you want to know is, how general is it? And it is very general. In other words, you can have any type of carbon attached directly to this halogen and be able to make it into a Grignard reagent. So it could be primary, secondary, or tertiary alkyl carbon group. It could be vinyl or alkenyl. It could be aryl, in other words, attached directly to an aromatic ring. Any of those things will work, and our 3 typical halogens also work to make Grignard reagents. So we want to know how we can use it, and we're going to write it like this. And so this carbon, in this first carbon that you come to in this R group that's directly attached to magnesium, has negative character. So the question I have for you is, well, when else have you seen a carbon with negative character? And we most recently did see that when we worked with terminal alkynes. We were able to make a terminal alkyne into an anion, and then what? What do we do with that? Well, you can use those terminal alkynes as nucleophiles or bases depending on whatever you put in there. And Grignards are no different. Once you have this carbon with negative character, it can either be a nucleophile or a base. And if it acts as a base, it's just going to pick up a hydrogen, and that will turn it back into an alkane, which is not necessarily something that you want, but you might. And it could be a nucleophile, and we're actually not going to study that until we get to a later chapter. So here's kind of an electrostatic map showing the Grignard reagent. So the end where the negative character is of course out there on the halogen, and then a little bit on the carbon end. And so this carbon right here now has some negative character. You see the redness down here. And the magnesium in the middle is all positive in character. And they used iodomethane in this case. For their R group is methyl in this case. And so it makes this particular Grignard reagent. So the next obvious question is, well, how good a base is it? And anytime we look at a base, we have a way to evaluate that. What is it? Well, by now, hopefully you realize that anytime we want to know how strong a base is, we look for the pK of the corresponding acid. And the acid that corresponds to the Grignard is the alkane. So we've seen some examples of carbon to hydrogen bonds and how acidic or not acidic are they in the last chapter. When we looked at terminal alkynes, we were kind of comparing those things. So here's that table that was from that chapter. And so if you had a terminal alkyne, the pK is about 25. Vinyl hydrogens about 44, and alkanes something on the order of 60. Now methane is the most basic, so other alkanes are in the 50s, not quite as high a pKa as methane itself, but nevertheless, if you're comparing alkanes, this is the strongest conjugate base. So alkane type CHs are not acidic at all, and so the corresponding anion is very, very basic. If you had a vinyl, remember I said that the Grignards could be used, could be prepared from even vinyl halides. Well, if you had that one, it's not quite as strong of a base as the alkane type Grignards are, but also very strong, and neither of those are quite as strong of a base as an alkyne, terminal alkyne. So they are very, very strong bases. So here's an example using 1-bromohexane. You can treat it with the magnesium. Remember I said there'd be a solvent, so the ether is the solvent. And you make the Grignard reagent. And this carbon right here now has a lot of negative character, and it will just pick up a proton. Now they just drew one of these hydrogens. It's just one of these hydrogens that's been picked up onto this, and so you make hexane back out of this. Now that doesn't necessarily look like something you'd want to do, because alkanes are not very reactive. They're pretty inert. Remember the terminology paraffin meant that it had a slight affinity. In other words, it's not very reactive. So you might wonder why would you do this, and a couple of things kind of come up. One of the things that's fairly obvious is if you don't want this reaction, you have to make sure that you don't let any water come into contact with your Grignard reagent. And later when we start using Grignard reagents as nucleophiles, we just have to make sure that we keep the flask and all the reagents very dry, or else it will kill the Grignard reagents, just making them into alkanes. And also, anything else that's fairly acidic, like an alcohol functional group or an amine functional group, a carboxylic acid, obviously, all of those will react with the Grignard and do an acid-base reaction with it. It doesn't have to be something that's nominally named blah blah acid. All kinds of things are more acidic than something with a pK up in the 50s. So you just have to be aware of that. If you're trying to do a Grignard that you want it to do something other than just be a base, you have to make sure no such things are present. And of course, lastly, if for some reason we needed to get a halogen out of the molecule, then of course we can use this. So it's a strong base. Sometimes you want a really strong base. So here's something else that you might consider. Suppose that you wanted to put a deuterium. Now D stands for deuterium. Remember what deuterium is? Deuterium is the symbol for a hydrogen. It's an isotope of hydrogen that has a mass of 2. So it has not only a proton but also a neutron in the nucleus. And where do we get that from? You might wonder where you could get it from, and there actually may be a couple of other examples that you've seen in the book and that I did not talk about. But you can get, instead of H2 molecules, you can have D2 molecules, And so if you did hydrogenation of an alkene with D2, you could introduce deuterium in place of alkenes. And you can also have heavy water, which is D2O, is called heavy water because it's got those extra massive hydrogens in place, deuteriums in place of just normal hydrogens. And the reason that people like to introduce deuterium into molecules sometimes is that then it provides like a handle on the molecule, so you could follow the fate of such a thing more readily in, say, an organism. If you're feeding plants or animals some labeled molecules and you want to know where in the tissues these molecules end up, having a label in there is a way to find it again. And so now we have a way to do this. We can react our alkyl halide with magnesium and then follow that with D2O, and that will replace this bromine with the deuterium specifically. And that's a fairly easy way to make, and not very expensive way to make a labeled molecule. So then you just decide, what you need. So if I start with this alkyl halide and I treat it with magnesium and D2O, well, this chlorine is going to get replaced with the deuterium. And so there's a picture of that. Now, this hydrogen was here already. It just wasn't drawn in. And so you might see this molecule drawn with just the D sticking out here. Because all the bonds that are not shown, the understanding is that they are bonds between carbons and hydrogens. So then what do you get if you just react with magnesium in plain water? Well, you just get back cyclohexane. Alright, so that's all we're going to do with Grignards for now, but we will be seeing them again before too many more chapters. A similar kind of thing can be done with lithium. But remember, magnesium's an alkaline earth metal, so it can either take the elemental state, which we represent with little superscript 0, or it can be +2. And so it was able to make a bond to the carbon and to the halogen. But lithium is an alkali metal. It can only go from either 0 or +1 oxidation states. And so that means that if we want to balance the equation and introduce this lithium into our organic molecule, we're going to have 2 lithiums for each organic compound. So here's the balance equation. So one of these lithiums is going to take the place of this halogen, and that's going to change the polarity of the carbon, just like the Grignard did, because now the carbon will have gone from having positive character to negative character once it's associated with that lithium. The other lithium is also going to get oxidized, and it will become a cation for the anion that you're going to lose out of here. So the lithiums are both getting oxidized to officially +1, and the carbon is getting reduced. Now this kind of bond is very polar. It's also still covalent, and these kinds of compounds can work exactly the same as the Grignard. In other words, you still need to keep water away from these things because you're still talking about a very strong base. You also still have a lot of different kinds of carbon that can do this, and also the variety of halogens. So far, everything is very similar to what we talked about with Grignards. It just balances a little differently. And so these things can be made just like Grignards, and they can be used as strong bases. In fact, this is butyllithium, or normal butyllithium, in butyllithium we call it, is frequently used as a strong base because you can actually buy that. You notice that it also has a solvent associated with it. And these can also be used as nucleophiles, so everything that we could do with a Grignard might be doable also with an organolithium compound, although some things we prefer the Grignard itself. But they're still strong bases, so we got to keep water away from them. But what we want to do with this instead is we want to kind of modify the organolithium compound. So we're going to take two of those organolithium compounds and react them with cuprous iodide. So this is copper in the +1 oxidation state. And it will make this species, which is called a lithium diorganocuprate. Now this is specifically in this reaction they show you with a methyl group, and so they call this lithium dimethyl copper. So it's lithium diorgano, the organo group here is methyl, and it's a copper, that's a name, and a cuprate is a class of compounds. And in the process you also produce a side set of ions from the lithium in the halogen. Well, so you've incorporated two of these groups onto this copper. And so the obvious question is, why do we want to do that? And if you go back to the periodic table that has the electronegativities on it, copper is a little closer to carbon in electronegativity. And so you still have a very polar bond between the carbon and the copper, but it's not as pronounced as it was between the carbon and the lithium because they're further away from each other in electronegativity. So, so that kind of thing can still act like a base, and so you still need to keep water out of it, but what it can be used for is for what's called a coupling reaction. So we can react this molecule that we just showed how to make up here with another alkyl halide, and they picked an iodide here, and that will couple together. So one of these chunks of carbon will take the place of this iodine, so you're doing a type of substitution, and it's called a coupling reaction because you're coupling this chunk of carbon together with this chunk of carbon to make this molecule. But you notice that some of your carbon is actually goes to waste, and there's really not much that you can do about that. Alright, a couple of other things. We call these lithium diorganocuprates, or sometimes also called Gilman reagents, because of the person that worked on this originally. And since you're wasting half of your carbon from your lithium diorganocuprate, then it doesn't really matter which one of these molecules was originally made into the lithium diorganocuprate. Remember, we started with back here on this previous slide, we started with an alkyl halide to make it into the organolithium compound, which ultimately turns into the lithium diorganocuprate. So either one of these starts as an alkyl halide, and so in this case they've chosen to make the lithium diorganocuprate out of the smaller number of carbons, because whatever is the lithium diorganocuprate, half those carbons are going to be wasted and only one set of them are going to be incorporated into your new bigger alkane. So we're going to summarize, and you see what's happening here is that we started out with two molecules of an alkyl halide, and to balance the overall equation I have a 1-to-2 ratio, but I'm going with 2 here because ultimately I need 2 of these to make the lithium diorganocuprate. So you have to balance it to get all the way to the end, we have to start with 2. And so once we react the organolithium with the cuprous iodide, we make the lithium diorganocuprate. Now I'm going to call this R prime. I react it with some other chunk of carbon in a form of an alkyl halide, and I make my bigger alkane, and part of my original alkyl halide carbons are lost to this compound that I don't want. So this is one way of writing it. So you're writing out each step along the way. Now you can kind of shorten that up, and you can say I'm going to take 2 alkyl halides, I'm going to react it with the lithium and the cuprous iodide, make the lithium diorganocuprate, and then the alkyl halide. So this is just shortening it up. It takes up less space. You know, we're all about taking up less space. And both molecules, the original alkyl halide and this alkyl halide, are going to go together in the ultimate larger alkane, by virtue of the fact that we've had the lithium and the cuprous iodide intervene on this molecule to make the lithium diorganocuprate, and then we can put them together. But we can't put them together until we treat the first one with the lithium and the cuprous iodide, because this carbon has negative character, this carbon has positive character, and that's why they go together. Alright, so let's practice again. Let's consider a type of problem sort of like our synthesis problems that we've been working on. So usually in your synthesis problem guidelines, you're told that you can have some things, including some molecules that only have 5 carbons or less. And in your synthesis problems that you've had to work on so far, you could either start with alkenes or alkyl halides, depending on which row you're on. Well, in the future, we'll start narrowing that down to fewer choices, and we'll only be able to start with either alkyl halides, or a little later we'll start with alcohols of 5 carbons or less, and for any row. It won't have differentiations depending on row. And so if this is our target molecule, and you wonder, could you use any of the reactions from Chapter 8 or 9? Now, what reactions in Chapter 8 or 9 am I talking about? Well, let's see. If you count how many carbons are in here, you have 1, 2, 3, 4, 5, 6, 7, 8, which means that if you're limited to molecules that have 5 carbons or less, there has to be a new carbon-carbon bond somewhere in there, and maybe more than one. And what kind of things do we have that we did in Chapters 8 and 9? Remember, I said you need a list of what reactions you have that make new carbon-carbon bonds. So we had the little reactions that make 3-membered rings. Well, there's no 3-membered ring in here, so that doesn't sound all that great. And then in Chapter 9, that was the terminal alkynes. Now, a terminal alkyne has a triple bond at the end of a chain, and those 2 carbons have 3 bonds between each other, which limits how much branchiness there can be. So if this is your target molecule, you don't have any carbons in here that are not branchy. In other words, you can't use an alkyne because you don't have any way to get branchiness into the vicinity of an alkyne, and there's no vicinity in here that's far enough away that would have worked in an alkyne. You may have to think about that for a minute, but it just won't work. And so this example is chosen specifically to eliminate that possibility. So this is where we can use the lithium diorganocuprate. And it doesn't matter where we break it. There's a lot of symmetry in here. So we could either make this bond and break it down into a 5 plus 3 problem, or that one, it's still the same 3 plus 5 problem, either way you look at it. And so we can have molecules of 5 or 3 carbons. And so if we want to take advantage of the lithium diorganocuprate, what do we need? We need alkyl halides. So we could have this alkyl halide, or it could be this one. Either way, it's the same thing. And this could have been a chlorine, a bromine, or an iodine. But we've already built in the right carbon skeleton. We've got our branchiness in here, and we're going to attach something here, and the new chunk of carbon is going to attach here. So we've already got part of our carbon skeleton is right. And so we need the other piece to be the 3-carbon piece. Again, we've already built in some branchiness. We need this middle carbon to be attached to the copper. And so we need 2 chunks of isopropyl groups attached to 1 copper. Now, in a synthesis problem, you will have been told that you could start with alkyl halides. Is this an alkyl halide? No. So when you ask yourself that question, what does that mean? Well, if the answer is no, that means you have to show where did it come from. So we know how to do that. We can make that from the organolithium compound. Is that an allowed material? No. But how do you get from here to here? Well, you put in the cuprous iodide. But this isn't an allowed starting material either, so we can get that from an alkyl halide, right? we treat the alkyl halide with lithium, and again, you can have any halogen you want here. I picked a chlorine just so we're not using the same one every time. Okay, so if your starting materials were alkyl halides, then now both pieces of carbon that got incorporated into the product match the requirements that you have alkyl halides of 5 carbons or less. Now, we also have some other material that we've learned in this chapter. What if your starting materials had to be alcohols? Could we make these molecules from alcohols? Well, now's a good time to practice. Remember, I told you these synthesis problems are pedagogical tools for practicing the reactions. So what do we need to do to decide how to do this? If we want to prepare these from alcohols, we need the 3-carbon alcohol, and we need to look at the degree of the carbon in order to decide what to use. And same thing here, we need the 5-carbon alcohol with the alcohol right here, and we need to look at the degree of that to decide what to use. So how can you do that? Well, for second degree, remember we said that if it was second degree and it's not too crowded, then probably you'll use one of those reagents that's able to do this directly, and for bromine we use PBr3. And for this secondary, again, it's not too crowded. For the chlorine, we had another reagent for that, and that was thionyl chloride. So now if your synthesis problem says that you have to start with alcohols of 5 carbons or less, you have all the tools that you need to be able to do that, and this is what a synthesis problem would look like that when you got done with it, where you had this as your target molecule. One other reaction is presented in this book in an effort to keep up with the current literature. Sometimes people have used the lithium diorganocuprates on aromatics, and I said that it could be aromatic, but they found that sometimes they don't work as well as the alkyl iodides, and so they've been trying other things. And so this kind of a molecule can be prepared, and you notice it's a little bit crowded, and that might affect your ability to do some of those other things. And here's another alkyl halide, and we're not really going to go into, where, you don't have to make that. We're not going to go into where did that come from. And this palladium material is kind of intervening here to cause this coupling. And so the boron comes off, and this whole chunk of stuff comes off, and you can couple these two rings together and make another kind of coupling reaction, but it's specifically for aromatics. Now, one other thing, we abbreviate a benzene ring as a group. It's called a phenyl group, and I know we haven't gotten to chapter 15 yet. But then to abbreviate that, to make it fit in a line of type, they abbreviate it with pH. There's some other abbreviations that people use sometimes, but that's what that is. So it's 3 of these benzene rings around a phosphorus, and then 4 of those associated with a palladium. And you don't really need to memorize all that, but you do need to recognize this coupling reaction. And this only takes the catalytic amount of that palladium compound to make this work. And one other kind of interesting thing, toward the end of this chapter, they have a review of redox levels of carbon. Now, I've put a lot of emphasis on redox levels of carbon already, and will continue to do so. But if you're looking for a place where it's kind of all summarized, this is it. Okay, so your alkane. So if you go from an alkane to an alkene to an alkyne, remember we're oxidizing because we're losing hydrogen. And if you introduce an oxygen in place of hydrogen, then that's another level of oxidation, which is this carbon and the carbon with the oxygen on it are at the same redox level, or if it's a halogen or a nitrogen. So anytime you introduce a more electronegative element, it has the same effect as introducing a double bond. Now, one thing you might reasonably ask is, Well, okay, they started out with 2 carbon molecules and they went to 1 carbon molecules, and it's just because they want to talk about just 1 carbon. So this, if you compare this carbon, this carbon, this carbon, and any of these carbons, you're doing a similar comparison. And as you go from alkanes to compounds that contain oxygen, then you could go across and say alcohols to aldehydes to carboxylic acids to CO2. You're increasing your redox level. Remember, CO2 is the most oxidized form of carbon, and alkanes are the most reduced form of carbon. Well, if you introduce a series of halogens, you can actually go to the same redox level as you do in CO2, which is kind of interesting. And you can also go across a series with nitrogen, so nitrile carbons are in a higher redox level than this, which is analogous to an aldehyde, is called an imine. And you notice that the carboxylic acid carbon is at the same redox level as the nitrile. So all these in this column are at the same redox level. And you should kind of have a feel for where you are in the redox level of carbon anytime we talk about a new functional group. Because remember, we're transforming between functional groups. So we've talked about reducing alkynes to alkenes, and see, there you go. It's a reduction. And we talked about oxidizing alkenes to aldehydes or ketones. We've talked about oxidizing alkynes. They went to carboxylic acid. So when you redox, you're going across instead of up and down. All right, so for this chapter, you should know how to make alkyl halides. And we learned a bunch more about the free radical halogenation reaction that was introduced in chapter 6. So now we know more about that. You need to understand that mechanism and the details of that mechanism. So the steps that are involved and the calculations, if you want to do estimate enthalpy, you can do that. You can draw a reaction energy diagram. Remember, this is going to go in 2 steps. So you should know all of that. We also talked about allylic bromination and what the allylic position is, how to find it. And then in the reaction, once it starts, you make radicals, and you don't need to know all the steps, but you do need to be able to identify the allylic radicals and draw the resonance structures so that you can tell what all the products are and whether they're the same or different as resonance occurs. And we said that reaction was really only useful for the simplest molecule, propene, or simple unsubstituted cyclic alkenes. Are the ones that can be useful in, say, a synthesis reaction used in allylic bromination. We also talked about reacting tertiary alcohols and some crowded secondary alcohols with HX to make alkyl halides, or if we had a methyl primary or most of the secondary alcohols, you could put in a chlorine with thionyl chloride, or you could put in a bromine or a chlorine with PBr3 or PCl3. We did not have a way to introduce an iodine into in the place of alcohols in this chapter, but we'll see that in the next chapter. And then this section of material we just finished, we talked about how to make organometallic compounds with magnesium, so that was the Grignard. And we talked about lithium diorganocuprate, so organolithium compounds, turning those into lithium diorganocuprates, and also the Suzuki-Miyaura reaction. All those make, these two make larger alkanes from smaller alkanes, and all we did with Grignards in this chapter was use them as bases. And of course the last thing that we just reviewed a little bit was the redox. So as I said, anytime you kind of want to get a feel for the redox level of things, you can flip back to this chart of redox levels. And that is the end of chapter 10.